Okay, welcome to this FMSP online revision recording. So we're going to be looking at Edexcel FP3 in this session, and in particular the sections on vectors and matrices. So let's just remind ourselves of the syllabus content for that first of all. So the first thing we have here is if we have two vectors A and B, we need to know how to take their vector product A cross B. So this means that suppose we have a vector A which has got components A1, A2, A3, so an X component, a Y component and a Z component, three numbers. Suppose we have another vector B which similarly has components B1, B2, B3, then we can form a new vector which is called A cross B, the vector product of A and B. And the way that we would calculate that is as follows. So for the X component, we take the determinant of the matrix formed by pushing these four numbers together, A2, B2, A3, B3. So that would be A2, B3 minus B2, A3. And similarly for the Z component, we push these four numbers together. So that's A1, B2 minus B1, A2. And then for the Y component, we take the four corners and push those together. We take the determinant, but then we have to reverse the sign on that. So if you imagine doing that, you would effectively be taking the value B1 A2 minus A1 B2. So this is another three-dimensional vector, and what you'll find is that it's perpendicular to both of A and B, and that's very useful in some vectors work, as we'll see shortly. And the other thing that you need to know about this is that if you take the length of A cross B, then that will be equal to the length of A times the length of B times the sine of the angle between them. So if you put A and B tail to tail like this, suppose this is B and this is A, then you have this angle between them theta, and that's the theta that's being referred to in this formula. What it also means is that if you were to put a copy of B here and a copy of A here to form a parallelogram, so this is also B, this is A, then the area of this parallelogram is the length of A cross B, because of course its height will be the length of B times sine theta with a base of length of A. You also need to know how to use that in problems involving points, lines and planes. You need to know this definition of a line, or this form of a line, using the vector product. So here R is your general point on the line, so let's just mark that as general point. That's its position vector. A is a point on the line, and that can be any point, and then B is the direction of the line, so it's a vector in the direction of the line. Let's just think about what this means. It means that, well, if R minus A cross B is 0, it means they're in the same direction, which means that the direction from A to R is the same as the direction of B. So that, if you think about those things together, it means that these points R must be on a line through A in the direction of B, and that's a vector equation of that line. We also need to know things about matrices, so how a 3x3 matrix or a 2x2 matrix is a transformation of either 3D space or 2D space. We need to understand the relationship between composing those transformations and taking the products of their matrices. The transpose of a matrix, this just means you reflect the entries in this top left to bottom right diagonal. So if this is a 3x3 matrix, these three entries will be reflected to these positions and vice versa. A 3x3 determinant, how to take that, how to take an inverse of a 3x3 matrix where the determinant is non-zero. You need to understand that taking the inverse of a 3x3 matrix corresponds to its inverse transformation, wherever that's possible to do. And then eigenvalues and eigenvectors and diagonal form. So the first question we're going to look at will actually involve us looking at eigenvalues and eigenvectors. So let's move on to that question. So here we're given a 3x3 matrix called M. Notice one of the entries is not specified, it's just given as K. We're told that this vector is an eigenvector of M. We've got to find its eigenvalue. We've got to show that K is 3. We've got to show that M has got 2 eigenvalues. And then at the end of the question we've got to consider the transformation represented by M, and we're considering how it moves a line L1 to another line L2, and given the Cartesian equation of L1 we're being asked to work out the Cartesian equation of L2. Okay, so let's start with that. Let's remind ourselves of what we mean by an eigenvector and an eigenvalue first of all. So if we have a matrix A, a a square matrix and a vector v, if we apply the matrix A to V and get a new vector which happens to be just a scalar multiple of V itself, so here lambda is a scalar and A is a matrix, then V is said to be an eigenvector of A, and lambda, this number, is the eigenvalue. So that's what we're looking for here. We're told that this is an eigenvector of M, and that should be sufficient for us to work out the eigenvalue and then K as well. So let's just have a look at that. So if 616 is an eigenvector, it means that if we apply M to it, we get a multiple of 616. So let's just have a look at what we actually get when we do that. So here's M, 1, 0, 3, 0, minus 2, 1, and K, 0, 1. Here's our vector, our eigenvector, 616. So if we do the multiplication here, what do we actually get? Well, for this number we do this row times this column, so that's a 6 and an 18, which is 24. For this number we're going to get negative 2 plus 6, which is 4, and then for this number it will be this row times this column, which is 6k plus 6. Now this equals a multiple of the original vector, and we can see straight away by looking at the x components and the y components that lambda here must equal 4. So we can say since 24 needs to be 6 lambda, this means that lambda is 4, or we could have got that from the y component, 4 equals lambda, but then that means we've got an answer for part 1. We've got the eigenvalue is 4. For part A. For part B, you can see that by looking at the z components, so for part B, we have to have 6 times lambda equals 6k plus 6. Well, now we know that lambda is 4, so this is 24 equals 6k plus 6, which is like saying that 6k is 18, which is like saying that k is 3. So k has to be 3 for all this to fit together and for this to actually be an eigenvector of M. So now we're going to move on and consider the other eigenvalues. Actually, we're going to show that it's got 2 eigenvalues. So a 3 by 3 matrix could have up to 3 distinct eigenvalues. This one's only got 2, and we need to show that that's the case. So let's just remind ourselves of how we do this as well. So if we've got a 3 by 3 matrix called A, we're going to subtract lambda times the identity from that matrix, and I'll explain what that means in a moment. We're going to take the determinant of that and set it equal to 0. That's an equation which is called the characteristic equation of A, and its roots, the values that satisfy it, are the eigenvalues of A. If A is a 3 by 3 matrix, then the identity is this one. It's also a 3 by 3 matrix with 1s down the top left to bottom right diagonal and 0s everywhere else. So what this actually means is you take away lambda from that diagonal on A. Okay, so let's have a look at how this works for our matrix M. And remember, we now know that K is 3 here, so we can always write 3 rather than K. So M minus lambda I, and then the determinant of that, and set that equal to 0. So we're going to have 1 minus lambda, 0, 3, 0, minus 2 minus lambda, 1, 3, 0, 1 minus lambda. We're going to take the determinant of that, and we're going to set it equal to 0. So to take the determinant of this one, I think I'm going to expand along the top row. So we'll have 1 minus lambda times the determinant of this 2 by 2 matrix here, and then minus this number times the determinant of this pushed together. That's going to be 0 anyway. And then 3 times the determinant of this 2 by 2 matrix here. So let's have a look at that. So we have 1 minus lambda times minus 2 minus lambda times 1 minus lambda, and then no contribution from this part, and then 3 times, and then it'll be the determinant of this one, so this will give us a 6 and a 3 lambda there, and that's equal to 0. This is the characteristic equation. So let's start expanding the first term. So we have 1 minus lambda, and then expanding the other bit, we've got minus 2, we've got minus lambda, plus 2 lambda, so that's plus lambda, and then plus lambda squared, and then we got plus 18 plus 9 lambda equals 0, and then expanding again, we've got minus 2 plus lambda squared plus 2 lambda minus lambda squared minus lambda cubed plus 18 plus 9 lambda equals 0. Okay, now I notice that I've got a negative lambda cubed here, so I'm going to move all of the terms to the other side by adding or subtracting in order to get a plus lambda cubed. So what will that be? We'll have lambda cubed, we've got these actually cancel, so there are no lambda squareds. We've got 3 lambda here and 9 lambda here, so that's plus 12 lambda, but on the other side minus 12 lambda. And then we've got minus 2 and 18, which is 16, but on the other side minus 16. So this is the characteristic equation of our matrix M. Now, we know that 4 is an eigenvalue, so 4 should satisfy this, and it does. So if we set lambda equal to 4, this is 64, take away 48, take away 16, which is indeed 0. But what that also means is that lambda minus 4 is a factor, so we can pull this out, and we need to work out what this quadratic will be, so that this times this is this. We can see this has to be lambda squared. We can see that this has to be plus 4 quite easily. To get the minus 12 lambda, well, we're going to have plus 4 lambda here. So let's just have a look at this. We're going to have, or rather to get no lambda squared, we've got minus 4 lambda, so it's going to have to be plus 4 lambda there. Yeah, so for the lambda term we'll have plus 4 lambda minus 16 lambda, which is negative 12 lambda, equals 0. And then I'll just move over into this space to finish this off. So we have lambda minus 4, and then of course this factorizes as lambda plus 2 times lambda plus 2. So the eigenvalues are the roots of this, so eigenvalues are lambda equals 4 and lambda equals minus 2. So it's only got 2 eigenvalues, 2 distinct ones. Lambda equals minus 2 is a repeated root of the characteristic equation. Okay, so now we're moving into the last part where we have to consider the transformation represented by M, and again remember it looks like we're going to be taking k equals 3 here, so we don't want to be working with k, we want to be working with the number 3. We have a line in Cartesian form, and of course these linear transformations will map lines onto new lines, and the line that L1 gets mapped to is called L2. We've got to find a Cartesian equation for L2. Okay, so strongly recommend here for this kind of question, you don't really want to be working with Cartesian equations. You'd really prefer to write that in a vector form. So you need to know how to do this, and the vector form means something possibly like this. So you have a point and then a direction. Now the direction is just these 3 denominators to form a vector. So that's 1, minus 3, 4. The point on the line, its components are the things that you're subtracting from x, y and z here. So that's going to be 2, 0 and minus 1. So you need to know how that works, and I'm not going to cover that in this session, but that's how you convert between these 2 forms for a line. So that means that our sort of generic point on this line has an x coordinate in terms of this parameter of 2 plus lambda, it has a y coordinate of minus 3 lambda, and it has a z coordinate of minus 1 plus 4 lambda. So what I'm going to do is I'm just going to apply the matrix M to that generic point and have a look at what the image of it is. So here's M again. I'm going to put my generic point here, so 2 plus lambda, minus 3 lambda, and minus 1 plus 4 lambda. And I'm going to multiply this out. So we're going to get 1 times this, 2 plus lambda, and then 3 of this. So it's going to be minus 1 plus 13 lambda for the x component. For the y component, we'll get plus 6 lambda, minus 1 plus 4 lambda, so that's minus 1 plus 10 lambda. And then for the z component, 3 of this, none of this, and 1 of this, so that's going to be 6 plus 3 lambda. Take away 1 plus 4 lambda, so that will be 5 plus 7 lambda. Now this shows me a generic point on the image line, so I can see then that the image line has got equation like this, -1, -1, 5, and I'll just change the parameter there from lambda to mu. Of course that doesn't really matter, but it'll be 13, 10, 7 for the direction, and in Cartesian form, which is the form I need for L2, so L2 is this. So remember, the components here give us the denominators, so we'll have 13, 10 and 7, and the things that we're subtracting from x, y and z will be these three numbers. So this will give me x plus 1 and y plus 1 and z minus 5. So that will be the Cartesian equation of L2 there. So let's have a look at the mark scheme for this. So we can see that in the first part we're using the fact 616 is an eigenvector, picking up 2 marks there. There's a method mark for knowing what this means, and then accuracy for getting the value of lambda. The third row gives us k equals 3, again 2 marks for that. Here is the characteristic equation, and we can see its factorization here, so there's some method and accuracy marks for forming the first form of the equation, then the simplification and the roots, and then finally to switch L1 into this parametric vector form and then apply the matrix to that general point, and then to reinterpret this, and of course there should be some numbers here, 13, 10 and 7 as a Cartesian equation, all worth 5 marks here. So for the parametric form, 1 mark, accurate application of the matrix to that, another couple of marks, and then getting back to the Cartesian equation accurately in the method, another couple of marks for that. Okay, so this question is about vectors and planes. So the first thing to say about this question, I guess, is that this form here is using i's and j's and k's. You can write those things as column vectors if you want, and I will tend to do that. We've got to find an equation of this plane in the form r dot n equals a number. Now r is the position vector of your general point, n is a normal vector, and then we can work out the number on the right hand side using any point on the plane. So this is a standard technique. Then we've got another point P, and we've got a line which goes through it perpendicular to the plane. The fact we've already got a normal will be helpful then, and we're trying to work out where that line actually cuts through the plane. And then we've got another point on the plane, and we're trying to work out how far it is from N to PR. So we'll need a diagram for that just to work out what's going on there. Okay, so to begin with, as I say, I'm going to write this plane in using column vectors. So this is a point on the plane, 3, 0, 1, and these two vectors are your two directions. So I've got plus lambda times -4, 1, 0, and then mu times 6, -2, 1. Okay, so I've got to get r dot n equals p form. Now the key thing here is knowing that n is the normal to the plane, a vector perpendicular to the plane. So to find that direction, you take these two direction vectors and you take their vector product. So I'm just going to write them down here, -4, 1, 0, vector product 6, -2, 1. So what do we get when we do that? So there'll be 3 numbers here. This number is the determinant of this matrix here. Imagine pushing those 4 numbers together. So that's just going to be 1. This number, similarly, the determinant of this matrix, that's going to be 8 minus 6, which is 2. This number here, imagine putting the 4 corners together to form a matrix and taking its determinant and then switching the sign on that. So it's -4, but switch the sign to +4. So this is n in this equation. So the general form then is going to be, well, r, which I'll write as x, y, z. Let's take r equal to x, y, z. So it's going to be r dot n equals a number p, and this is n. So we have x, y, z dot product 1, 4, 2 equals p. So this is x plus 4y plus 2z equals p, and this should be satisfied by every single point on the plane. Now 3, 0, 1 is on the plane if you imagine lambda and mu both being 0. So I'm going to substitute in x equals 3. Whoops. I'm going to substitute in x equals 3, y equals 0, z equals 1 into this equation. So that will give me 3 plus 0 plus 2 equals p. So this means that p must be 5, and it means that my equation in that form is x plus 4y plus 2z equals 5. Okay, let's move into the next part of the question. So now we've got a point called P, and it might be worth drawing a diagram at this point. So maybe if I try to imagine that my plane looks like this. So this is part of my plane pi, and then we've got 6, 13, 5, which is not on the plane. You can easily check that that won't satisfy that. The numbers are too big to make that right hand side 5. And we've got a line L which is going through P perpendicular to the plane. So if you imagine it sort of passes through like this and makes a right angle there, and we've got and it intersects the plane at N. So this point here is called N. Okay, so I think what we need to do here is we need to write down an equation for that line. So a vector equation of this line. I'll call it L1 in my diagram. So again, we'll just use R as the position vector of a point on that line. So we can use 6, 13, 5 as the point, because we've been given that, may as well use it. And then plus, let's call it S, so we'll call this our parameter S, times the direction of that line. Now the direction can be the normal to the plane. We can see this line is supposed to be perpendicular to that plane. So if we go back to our previous work, remember that 1, 4, 2 is that direction. So we can just have 1, 4, 2 here. Okay, so this means that a general point on our line here, L1, has got x coordinate 6 plus s, has got y coordinate 13 plus 4s, this is, and has got z coordinate 5 plus 2s. So as we vary s, we'll pick up all the points on this line. Now we're trying to work out what value of s actually gives us n here. So this is when that actually is on that plane. So remember, the equation of pi, this plane that we got in the first part as well, was x plus 4y plus 2z equals 5. So all I need to do is substitute these expressions for x, y and z here, here and here, and that will give me an equation from which I can work out s. It will just have s's alone in. So substituting in gives us 6 plus s, and then we got 4 of this one, so that will be 52 plus 16s, and 2 of this one, so that will be 10 plus 4s equals 5. So we have 16s, 20s, 21s, 21s, 6 and 52 is 58, and 10 is 68. So we get this. So this means that 21s is minus 63 and s is minus 3. So this is the value that s needs to take in order to get the coordinates of n. So n is, and this is just by substitution of s is minus 3 here, it's going to be x is 3, y is 1, and z is minus 1. And we've got that correct answer there, 3, 1, minus 1. Okay, now we've now got a point R on the plane, and we've got to get the perpendicular distance from N to the line PR. Okay, so let's just draw a diagram of this. So once again, here's our plane. Here's our point P, which is 6, 13, 5. We've got this line L1 from before, you'll remember. That was, we calculated the equation of that. This is N here, which is 3, 1, minus 1. And now we've got another point on the plane called R, whose coordinates are 1, 0, 2. So we're thinking about PR, and we're trying to get the perpendicular distance from N to PR. So in my diagram it would be like a line here which forms a right angle here, and I'm trying to work out how long this short line here is for the final 3 marks in this question. Okay, so I think I can do this using some standard vectors techniques and trigonometry. If I can work out this angle here, I can just use standard trigonometry with sine to work out how long this is, because this side here is opposite this angle, and if I know the hypotenuse I can just use sine there. Okay, so the question is, how do I work out this angle here? Well, if I work out the vector PR and the vector Pn, I can use the dot product to work out the cosine of that angle. Okay, so let's have a look at that then. So PR in my diagram is the vector -5, -13 and -3, and Pn is the vector -3, -12, -6. Okay, so from the dot product I know that PR dotted with Pn will be equal to the length of PR times the length of Pn times the cosine of the angle between them, which in my diagram is up here, theta. Okay, so if we look at PR.Pn, we're going to get -5 times -3 is 15. Then we're going to get -13 times -12, so that's going to be 156, and then we've got 3 times 6, which is 18. The length of PR, so we need to use Pythagoras in 3 dimensions here. We're going to be squaring the -5, squaring the 13 and squaring the 3. The length of Pn, similarly, squaring the -3, squaring the 12 and squaring the 6, and times cosine of theta. Okay, so here then we've got 164, 174, 189. Yep. So this is 189. This is the square root of this number here is the square root of 189, and here we have 172 plus 25 square root of 197 cos theta. So what we can do with this is we can work out cosine of theta from this as 189 divided by the square root of 197 times the square root of 189, and then from that you can go on to work out sine theta, and then the length of this line here will just be this hypotenuse here, which is the length of Pn. So the answer will be the length of Pn, which is the square root of 189 times sine theta. So just to mention, the way that you would get sine theta from knowing cos theta, where you can use cos squared plus sine squared equals 1 for that, and anyway to 2 decimal places, or to 3 significant figures, you get 3.61 for this. Okay, so let's have a look at the Mart scheme here. So you can see, first of all, this is the equation of our plane, which will of course be x plus 4y plus 2z equals 5. We have our point here, which we saw, so that was worth 5 marks. So you've got some marks for the vector product here. You've got another mark for working out the right hand side, and an accuracy mark there for that. To work out the coordinates of where that line perpendicular to the plane actually cuts through the plane, well, first of all you need to form the equation of that line, worth a mark. Then you need to be able to work out the value of t at that intersection. There's a couple of marks for that, and then finally actually working out the coordinates for one final mark. And here we've got using the dot product to work out the angle NPR, and then using sine of that angle with the hypotenuse to work out the length of 3.61. Okay, so hopefully you found that useful. Here's a reference to our website. There's lots of other revision recordings there, and similarly there's another 3 recordings for Edexcel FP3.